Hey guys, this is John. In today's video, we're going to solve Laplace's equation inside a circle. This is the third video of a series about solving Laplace's equation on various different types of surfaces. So let's get started. So step 0 is draw the shape. Okay, so let's read the problem. So we're told that we have to solve Laplace's equation, cool, theme of the video, inside a quarter circle. Okay, so we're told that the quarter circle has a radius 1. So let's draw it up. So quarter circle, radius 1. So let's call this 1 right here. And then we're told that it goes from angle 0 to pi over 2. So let's call this 0 and let's call this pi over 2. Okay, so we're going to work in polar coordinates here. This is 0. Let's emphasize the boundaries of this quarter circle. Okay, so we're also told that the quarter circle at angle 0 is equal to 0. So partial at the first derivative, r 0 is equal to 0, and then we're told that this quarter circle at pi over 2 is equal to 0. Cool. And then we're told that we have this initial condition, or boundary condition, u1 theta is equal to f of theta. Cool. So now what we're going to do is separate variables. So in order to do that, what we're going to do is take the Laplacian u, and then separate it into its corresponding r and theta components in polar coordinates. Conveniently, we're given this nice hint right here, and we're also given the Laplacian of u, right? We're told that if we define, so they basically already separated variables for us. Let u r theta simply be equal to phi of theta times g of r, and then they have plugged in the value for u already, and then they just simply tell us that the separation of variables for u is going to look like 1 over g times r times d dr, r dg dr equal to negative 1 over phi d squared phi d theta squared. Okay. So how do we decide what we want our separation constant values to be? So what we want to do now is think about our boundary conditions. So our boundary conditions in theta, our BCs in theta are homogeneous, right? So I'm going to highlight them in yellow right here, 0 and 0 in theta, okay? So therefore, we want our function phi of theta to be oscillatory. Cool. So therefore, with just this conclusion right here, we can decide what we want our value of the separation constant to be. We want it to be positive in order to satisfy the right-hand side of this equation. What about the circle in green is the equation for phi, and if we solve this out, we're going to get solutions that are oscillatory. Cool. The left-hand side of the equation is a little more tricky, and that's going to come along and still work out properly with our definition of the separation constant. But remember that the separation constant has to satisfy both sides, but since we satisfied the right-hand side of this equation so far, we can probably make a logical conclusion that we have satisfied the left-hand side. Alright, so now what we're going to do is we're going to solve the differential equations. Let's quickly mark that down. Solve the diff EQs. Okay, so let's first solve the right-hand side. So phi of theta, let's not get ahead of ourselves here. So we're currently going to solve the differential equation. Negative lambda phi. So the first case we're going to look at is when phi is greater than 0, because phi can be less than 0, equal to 0, or greater than 0. Okay? So in this case right here, phi, if we solve this differential equation, is simply going to be equal to c1 sine square root lambda theta plus c2 cosine square root lambda theta. Our boundary condition tells us to evaluate this at its derivatives at 0 and pi over 2. So if we take the first derivative of this function right here, our equation, we find that we get c1 square root lambda cosine square root lambda phi minus c2 square root lambda sine square root lambda theta. So let's evaluate the first boundary condition. So at 0, we're told that this equation is equal to 0. So therefore, if we plug in 0 for theta, we find this at c1 square root lambda theta. Yes, so c1 square root lambda. Lambda is a real number that's greater than 0. So therefore, c1 must be equal to 0. Cool. Now let's evaluate the other boundary condition. So first derivative at pi over 2 is equal to 0 is equal to negative c2 square root lambda sine square root lambda phi. So, like earlier, lambda is still greater than 0, but if c2 equals 0, then this would mean that phi is trivial, which doesn't really help us here, right? Because remember that phi is just going to be 0 everywhere, which doesn't really tell us anything. So therefore, we're going to look for zeros in other areas, such as in the sines. So we want this function to be 0 once in a while, but not all the time. So when is this going to be equal to 0? This function will be equal to 0 for when square root lambda phi is pi over 2 is equal to n pi. And then lambda is just going to be equal to 2n squared. Cool. And then this tells us that our differential equation is going to be equal to c2 cosine 2n pi. The theta, sorry. So like I was saying earlier, right? If c2 was 0, right? If c2 was 0, then over here, where I've drawn this arrow, this would tell us that phi of theta is equal to 0. And that's just trivial, and that doesn't really give us any helpful information. So we're looking for other solutions rather than just the classic old equal to 0, because, like, that doesn't really help us. So let's take a look at when lambda is equal to 0 now. So when lambda is equal to 0, we have the differential equation d squared phi d theta squared is equal to 0. And if we solve this out by integrating both sides twice, we find that phi of theta is simply going to be equal to c3 phi plus c4. Okay? If we plug in the first boundary condition, which tells us the derivative, right? So the first derivative at 0 is just going to tell us that c3 is also equal to 0, right? But phi prime at pi over 2 is also equal to 0, but we just showed that c3 was equal to 0. So consequently, after applying the boundary conditions, we find that phi of theta is just equal to c4. And since this is not just the trivial solution, right, so phi of theta is just not simply equal to 0, this means that phi equals 0 exists. Okay? And since phi equals 0 exists, these n's, remember these n's are integers, these n's can start from 0. So n equals 0, 1, 2 to infinity, right? So if lambda equals 0 was not allowed, if lambda equals 0 was not allowed, then we would start from n equals 1. But since it is allowed, we start from n equals 0. Cool. Alright, so let's take a look at the case for when lambda is less than 0. because this may not be completely obvious at first. Okay, so we're going to return to our original differential equation. But now we realize that lambda is a negative number, right? So lambda itself is just a variable, but the value of lambda is negative. So for the sake of convenience, let's call lambda equal to negative s, right? So the reason why I'm doing this is that it's a little bit easier to work with because we know that lambda is inherently a negative number, right? So if we take the absolute value of lambda, it's going to be equal to s, and let's just put the negative sign on the outside and work with that instead, okay? Just follow along with what I'm doing right now, and hopefully it'll make sense. So now we've gotten rid of the external negative sign. Okay, so when we solve this differential equation right here, we get that phi of theta is going to be equal to some linear combination of sinh and cosh. So c5 sinh square root s theta plus c6 cosh square root s theta. And if we plug in our boundary conditions now, right? So the first one being phi, derivative of phi at 0 is equal to 0. This tells us that if we take the derivative of the function above, the equation above, we're going to get c5 square root s times 1, because cosh at 0 is just 1, and because s is non-zero, c5 must be 0. Cool. So let's take a look at the other boundary condition now. So derivative at pi over 2. So the derivative of cosh is just simply sinh, no negative. So we get c6 square root s sinh square root s theta. Sorry, pi over 2 equals 0. However, right, so square root of s is non-zero. Let's write in a different color. Non-zero. And sinh of this non-zero number, right? Remember the graph of sinh. Sinh looks like this. And that sinh is only 0 at 0, right? Since what we're evaluating the sinh function at, right? At a non-zero number, okay? We are evaluating sinh at non-zero. Therefore, sinh is not equal to 0, okay? So this entire thing is non-zero. So therefore, in order to satisfy this equation, c6, the constant, must be 0. c6 must equal 0. And if we put this all together, this just tells us that phi of theta is equal to 0. And this is just the trivial solution. And that literally tells us no useful information. So therefore, lambdas cannot be greater than, cannot be less than 0. Okay, so this is how you case through all of these. And for most problems, they will not be less than 0, and you'll usually be told whether or not they're greater than or equal to 0 or blah, blah, blah. So you don't have to necessarily show these cases. But there have been exam questions in the past that ask you to show why they can't be less than 0 or something like that. So it's important to know what we're doing here. Okay, so now let's go on to the second part of this diffie-q. So we've solved for phi. Now we have to solve for g of r. Cool, let's go about that. And now we know that for g of r, lambda can either be greater than 0 or lambda equal to 0. And we already proved that lambda cannot be less than 0, so we don't have to worry about that case. So let's go back to this differential equation. So this diffie-q right here, let's just copy and paste this down to make this easy, is equal to lambda g. Okay, let's expand this left-hand side. So if we're taking the derivative of two things multiplied by each other, we have to do the chain rule. So this is going to turn out to be r d squared dg dr squared plus dg dr. So this is just going to be r squared dg dr squared plus r dg dr is equal to let's move everything to the left-hand side. Minus lambda g equals 0. Okay? And then we know the value for lambda. So let's look at the case where lambda is greater than 0 first. Okay? We know the value for lambda. Lambda is equal to 2n squared when lambda is greater than 0. This equation right here should look familiar to you. This is an example of Cauchy-Euler. Nope. And we can solve this by plugging in a trial function for g, but I'm going to skip these steps for now and just show you what the actual solution is. So I think we're on constant C8 now, I believe. Yeah, C8. So the solution for g here is going to look like this, where we have r to the 2n plus cn r to the negative 2n. Cool. And this is for when lambda is greater than 0, as I said earlier, right? So now there's a new boundary condition called the boundedness condition, okay? So the boundedness condition essentially states that at the center of the circle, so if we draw a full circle here, I know we're working on a quarter circle, but this is for any problem where we contain the center, right? At the center in polar coordinates, we have a singularity, right? So in polar coordinates, we're undefined at the center. So consequently, we need to make sure that our function does not become singular at the center, because when we have heat flow isn't singular / undefined at the center. Okay? So at 0, right, our function for g cannot be, at 0, g of 0 cannot be undefined, because otherwise that wouldn't make any logical sense. How is heat flow undefined at the center, right? So if we start looking at g0, right, we have C8 of 0, 2n, plus C9 of 1 over 0 to the 2n, right? So here's where the issue arises. For this term right here that I'm about to circle, right, as we approach R0, this blows up to infinity. Okay? And we don't want that, because that doesn't make any logical sense. How is heat flow infinite at the center? So therefore, we're going to say that we're going to force C9 to be 0, because we don't want our solution to blow up, right? So g of r is going to be equal to C8 r raised to the 2n, where Cn is equal to 0 for like all intents and purposes, so that our solution does not misbehave at 0. Okay. So now let's take a look at when lambda is equal to 0. So to appropriately look at this case, we're going to go back to the original differential equation up here. I think this is the easiest way to show this. Okay, and then we're going to set the right-hand side to be equal to 0, right? So now we're going to divide both sides by r, and then we're left with this, right? So now let's take the integral of both sides with respect to r, and that leaves us with this relationship right here. Since we're taking an undefined integral, we're going to have this random constant. I think this would be C9 now. C9, yes. Wow, a lot of constants. Divide both sides by r, and then integrate once again with respect to r. And then what we end up here is with a natural log term, very interestingly enough, with another undefined constant. So what do we do with this natural log term? So going back to what I was talking about earlier about the singularity condition, right? We have to make sure that at 0, our solution does not explode. So once again, at 0, make sure sol doesn't explode, right? So at g of 0, we cannot have a solution that goes to infinity or is undefined, right? And what do we notice? the natural log of 0 is undefined. It just goes to infinity and explodes. So this is bad, right? And how can we amend this? By making C9 equal to 0 and then completely ignoring the natural log term. So therefore, g of r is just equal to a constant term, C10. Cool, so we're all set now. So we have solutions for lambda equals 0 and then lambda greater than 0 for g of r. So now we can put our solution together. I think this is step 2. Yeah, that was a long step 2. Step 3. Put it all together. Remember that we defined u of r theta to be equal, well, the book defined it as phi of theta times g of big G of r. So consequently, we're going to multiply everything back together. So we have, for our lambda equals 0 case, let's put that first to make it nice and explicit. So for lambda equals 0, we're going to have a constant term right here. So at lambda equals 0, our phi function is equal to a constant. And then for lambda equals 0 for g, we're just also simply equal to some arbitrary constant. So what we're going to do is we're going to combine these all together, these two constants together, as one big constant called a0. Okay? Then we're going to account for when, let's mark that as lambda equals 0 terms. Okay, remember that we're multiplying two arbitrary constants together, so we can define them as a new arbitrary, bigger constant, essentially. Okay, now we're going to account for the other terms. And what we're going to do is apply the principle of superposition. Right, so we're taking an infinite linear combination of the other solutions for all non-zero lambdas. Okay, so then this is going to be the product of two different functions now. So when lambda is greater than 0, we have this function multiplied by this function right here. Cool. So once again, we're going to call those big constants, the little constants, and we're going to put them together into one big constant called a of n times sine 2n theta times r, I believe it's 2 to the n. Right, so this is going to be our that's going to be our phi of theta terms, and this is going to be our g of r terms. And these all account for all lambda greater than 0 terms. Cool, so this pretty much comprises our final solution for our for the general solution for the u. Okay, but we still have one more step to go, which is to find the coefficient values for a0 and an. So step 4, find coefficients. And going back to orthogonality principle again, what we're going to do is simply do what we've done before. So the initial condition, or boundary condition, because there's not really time in this case, so we could just call it a boundary condition, u of 1 theta is equal to f of theta. So if we plug in 1 is equal to a0 plus summation n t equal 1 to infinity an sine 2n theta of 1. So 1 to the any power is just 1, so we can just leave that out. Okay. So our first problem here is finding the coefficient value for a0, and if you've watched my orthogonality video, or if you've practiced enough, you should be able to pluck the solutions just by looking at these. So the solution to a0 for this specific case is going to look like 1 over the total path length. So the path length being pi over 2, so 2 over pi, times the integral of pi over 2 f theta d theta. And then an is going to be very similar, f of theta times sine 2n theta d theta over 2 pi sine squared 2n theta. So these are our final coefficients for this problem. And then your final solution would be just simply be comprised of the starred things right here, and you would basically write these two things together. If you guys have any questions, comments, or concerns, please let me know in the comment section below.